In the last video, we explored how we can compare integrals in infinite series, and we can use the integral to come up with upper and lower bounds for what a series must converge to if it converges, or show that it diverges, again, by virtue of a comparison. So today we're going to, in this video, we're going to formalize those results in a theorem called the integral test. The integral test says the following: suppose that an is a sequence, and its terms are given by some function f of n, where there's three stipulations. F, it must be positive. So all the terms, y values are greater than 0. It is decreasing. All right, so f of n is greater than or equal to 0. Decreasing means f prime of x is less than 0, or less than or equal to 0 for x greater than 0. And lastly, it is continuous, meaning we don't have any asymptotes, we don't have any jumps. F is defined everywhere. So if those three properties hold, then we can say the following: if the integral from 1 to infinity of f of x dx converges, then the sum from n equals 1 to infinity of an converges. And similarly, if the integral of f of x dx diverges, then the sum must diverge as well. In other words, the integral and the sum must do the same thing. Okay, so if we can figure out if the integral converges, which often integrals we're going to find are easier to work with than series, then we can determine exactly what the corresponding series is going to do. As long, again, as these three stipulations hold, the function needs to be positive, decreasing, and continuous. And if you think about the examples that we looked at last time, both of those had the same sort of shape. The function was positive, all the y values were above the axis, it was decreasing, and there were no jumps. Again, that only has to apply for x greater than 0. All right, so let's see if we can apply that result to a couple of examples. So let's look at the sum of 1 over n to the 3 halves from n equals 1 to infinity. And we'd like to determine if that converges or diverges. And according to the integral test, if the corresponding integral, which would be the integral from 1 to infinity of 1 over x to the 3 halves, converges, then the sum converges. And if that integral diverges, then the sum must diverge, as long as these stipulations are satisfied. And you can easily check, but that is positive, decreasing, and continuous. So we can indeed apply this theorem. You could easily graph out 1 over x to the 3 halves and verify that those three things are true. All right, so let's evaluate the integral. The integral would be, this could be written as x to the negative 3 halves. And so the antiderivative, we'd have to increase the power by 1. And then multiply by some constant, which I think negative 2 would do the trick. And at that point, we have, let's see, if we take a derivative, negative 1/2 would come out front, and that would cancel the negative 2. So I think that does check out. All right, and so another way of writing that would be negative 2 over the square root of x from 1 to infinity. And if we plug in the endpoints, we will have negative 2 over infinity plus 2 over root 1, which is this term wants to go to 0 because the denominator is growing, and the second term wants to approach 2. So since the integral gave us a finite answer. It converged. The sum must converge as well. All right.